tutorial on bend allowance. What exactly is bend allowance? When a sheet is bent in a press brake, the region of the sheet close to and in touch with the punch elongates to compensate for the given bend. If you compare the length of this part before and after the bending, you're going to find that they are different. As engineers, if we don't compensate for this variation, the final product or part won't have accurate dimensions. Of course, this is more critical for parts where you have to maintain a tighter tolerance or precision. Of course, this video is by no means an exhaustive discussion on metal bending theory. However, we do cover some of the basic principles that engineers face in real-life work every day. Before I start, let me say one more thing. There isn't really a scientific method to exactly predict bend allowance, due to the many different factors at play. For example, actual material thickness, tooling conditions, forming methods, and so on. There are so many variables here. In reality, many methods are used. Trial and error is a very popular one. In addition, people can use bending tables taken from engineering books and metal suppliers and manufacturers. Some companies will develop their own bending tables based upon their own standard formulas, and so on. But let's get back to SolidWorks. How does SolidWorks calculate bend allowance? Well, SolidWorks uses bend allowance and bend deduction. What are these methods? We're going to spend a little time explaining those here. The bend allowance method is based on the following formula. The total length of the flattened sheet is equal to the sum of lengths 1 and 2 plus the bend allowance. The bend allowance region, here it's shown in green, is a region where, in theory, all deformation occurs during the bending process. Generally, bend allowance will be different for each combination of material type, material thickness, bend radius, bend angle, and different machining processes, machining types, machining speeds, and so on. The list of variables is really endless. The value of bend allowance that comes from sheet metal suppliers, engineering books, etc., is provided in bend tables and looks something like what you see on your screen here. The bend table approach is probably the most accurate approach because you can put the data in manually. Or, if you're not sure of the bend allowance value, you can always run tests. You'd take a piece of shredded metal that you'd be using for this part, exactly the same. Then you'd bend it using the identical process you'd use for machining. Simply take your measurements before and after bending. Based on this information, you'd adjust the bend allowance as needed. Another method is the bend deduction method. The formula is as follows. The flattened length of the part, shown right here, equals D1 plus D2 minus the bend deduction. As with bend allowance, bend deduction comes from the same sources, tables, manual testing, etc. Obviously, it's easy to see how these methods are related to each other based on the formulas that we see right here. Another method for calculating bend allowance uses the K factor, where K is the neutral axis offset. The general principle goes like this. The neutral axis, which you see here in red, doesn't change during the bending process. During the bending process, the material inside the neutral axis will compress, and the material outside the neutral axis will stretch. The neutral axis will be closer then to the inside bend, as you see here in blue. The more the part bends, the closer the neutral axis will lie to the inside of the part. The K-factor, as we see here, equals T, or the offset distance to the neutral axis, divided by big T, the thickness of the material. In this formula, the bend allowance equals 2 pi multiplied by A, the angle, multiplied by the sum of R, the bend radius, plus the K-factor multiplied by T, the thickness of the material. Divide all of this by 360. In theory, the K-factor can be between 0 and 1, but for practical purposes, it's more like 0.25 to 0.5. For example, you will find that hard materials, such as steel, have a higher K-factor, such as 0.5. Softer materials will have a lower K-factor, closer to 0.25. Copper is an example of a softer material. One last point. The wiped hem on this part has a K-factor of something like 0.3. On the other hand, a soft or gradual and larger bend has a higher K-factor of about 0.5. And this concludes